there for like watching them.
Alrighty. Good morning, everybody. Welcome back to Calc 1. Plan for today is we are going to continue our discussion of Standard 5, looking at properties of derivatives, looking at a few more theorems that make derivatives a little bit easier to calculate. As far as office hours go, I've got my usual office hours on Monday, 11 o'clock and at 2. And as far as homework goes, I posted another web work assignment, homework 7, that will be due on Wednesday. And the plan is to have a quiz on Monday over Standard 5. So, got a big pile of stuff to pass back, including a bunch of retests from the past few days. With that in mind, Hannah, C. Paul, Tyra,
I always skip the last 3
Aiden,
That's what I did. That's exactly what I did. That's exactly what you should. Especially because that's what is this thing?
Riley,
I did some setups. I did some setups for now.
Joseph, Will, Emily, Cecilia, Rachel, Benedict, Mackenzie, Avery, Petro, Laura, Elise, Helen, Sarah, Win, John, Ryan, Logan, let's see, okay. I'll have solutions up over the weekend for the standard 4 quiz. Haven't quite yet posted them. I'll try to post them after class today. Okay, so what is the only cure for a bad case of the right angles? The only cure for a bad case of the right angles is the Pythagorean theorem. Okay, so last class we talked about defining the derivative of a function as being a function itself, where we said given a function f of x, f prime of x is going to be the function that gives us the instantaneous rate of change of the original function at every single point. And we talked about how you can calculate that using the limit definition of the derivative. And then towards the end of class, we said we were going to start talking about some shortcut rules for how to calculate derivatives a little bit more efficiently without having to resort back to that limit as h goes to 0 of blah, blah, blah every single time. And the big rule that we looked at towards the end of class was the power rule, which says that if you have a function f of x that's a power function, meaning its f of x is just x to some power, like x squared, x cubed, etc., then the derivative is going to be n times x to the n minus 1. Meaning to differentiate, we pull down a factor of n out in front and then subtract 1 from our exponent. So we looked at some examples of putting the power rule into practice last time. So I thought what we could do today is to start by seeing if we could sketch a little bit of a proof of why the power rule is true. Because it's this nice, cool formula that's very useful to use, but it doesn't really seem to be very intuitive to me of where does this nx to the n minus 1 formula actually come from. And so I wanted to do a quick little proof sketch of why does this formula happen the way that it does. So by definition, we could say that if f of x equals x to the n, where n is some power, we could think about taking this as being f prime of x. If we were to use the limit definition, it's going to be a limit as h goes to 0 of the expression f of x plus h minus f of x all over h. That was kind of our definition on the front page of how we compute the derivative of an arbitrary function f of x. So what would f of x plus h be in this example? I mean, if we were to plug in x plus h into our original function f of x, what would we come up with? Rachel?
X plus h to the n.
Yeah, the quantity raised to the nth power. I like it. So we're going to get x plus h raised to the nth power. And then minus f of x is going to be minus x to the n all over h. And so if we want to take a limit as h goes to 0, we're going to need to evaluate this expression, x plus h to the n. So true or false? Can we take x plus h to the n like this and write it as x to the n plus h to the n? I feel like I'm seeing some yeses, I'm seeing some nos. Cecilia, what are your thoughts?
I don't think we can, because if you FOIL the x plus h to the n, I think it'd give you a different answer than if you just raised x to the n and h to the n.
Yeah, if we had, for instance, n was 2, then when we took x plus h quantity squared, we get something like x squared plus 2xh plus h squared. So we cannot do this. This is bad. Do not do it. Life does not work out as nicely as that. You do that with multiplication. If we had something like x times h to the n, we could split that up into x to the n, h to the n. But we can't do that but exponents don't break up nicely over sums like this. So here's what we're going to do instead. If we were to take x plus h times x plus h times x plus h n times, without knowing any information about n, well, we're going to have an x to the n term, just from taking the x term and multiplying by itself n times. Kind of the first piece of the sum is always going to show up. We're also going to have a term that, if we were to multiply this out, is going to have an h n x to the n minus 1. That's going to be sort of our x to the n minus 1 term that'll pop out if you multiply this all out. And then we're going to have lots of terms with h squared factors. Basically, every other term in this sum, when we multiply it out, x plus h raised to the nth power, is going to have something that has factors of h squared in it. You might be thinking, Dr. Gerstle, what are all of these h squared terms? They're heavily dependent on n. I don't feel like trying to write out a general expression here. And as it's going to turn out, those terms are not going to really matter in the end. Angela, you have a question? Okay, you sort of had your hand up. So we have all that, and we're still going to be subtracting off x to the n and dividing by h. So this was the expression we got when we took x plus h raised to the nth power, and we still subtract x to the n and divide by h. So what can we do with this expression? When?
First, you should cancel out your x to the n.
We have a plus x to the n and a minus x to the n. Those will cancel out nicely. I don't see anything else in the numerator here that's going to necessarily cancel out right away.
Can you factor out an h from the top?
Okay, so what's the factor out in h? So if we did that, we get h times, let's see, this term would give us an nx to the n minus 1. But what happened to all of these terms with factors of h squared in them? If we factored out an h.
They'd all just be times h.
Yeah, if we since all of these have h squared factors in them, we can pull out a factor of h, and what's left should still have at least one factor of h in it. So we can write this as nx to the n minus 1 plus lots of terms with h factors. Because if I took a term that was something like, I don't know, h squared times x, for instance, and pulled out a factor of h, what's left is still going to have at least one h in it, so to speak. Okay, so we have h times nx to the n minus 1 plus lots of terms with h's in them, all divided by h. I think we can give this the old swoosh, swoosh. So we have nx to the n minus 1 plus lots of terms with h factors. And now, what's going to happen if we take a limit as h goes to 0 of what's left? Well,
We're just gonna have nx to the n minus 1.
what happens to all these terms with h factors?
So if we plug in 0, then they'll all be 0.
So as h goes to 0, all of these terms are going to go to 0, so the nx to the n minus 1 is going to be all that's left? I like it. Yeah, because as h goes to 0, it's going to give us nx to the n minus 1 plus lots of terms with factors of 0 now. And then, of course, if you have a factor of 0, 0 times anything will give you 0. And so we do, in fact, get nx to the n minus 1 as our final answer. So technically, this only really works if n is a positive integer, like n is 2, 3, 4, 5. Yesterday we were doing the power rule with examples like, what if f of x equals x to the negative 5 power? Or f of x equals x to the negative 3.5. And technically, if we did that, we couldn't split up x plus h to the n in this way. But I still thought it would be good for you to kind of see somewhat of a proof that the power rule works the way it does. Just to kind of help illustrate that this formula, x to the n has a derivative of nx to the n minus 1, formula doesn't just come out of nowhere. It's not like something that's just magic. It is actually something that comes from using the original definition of the derivative. And once we know this result, we can just use it going forward as sort of our shortcut method. Any questions, comments, or concerns? Gosh, Gosh, Dr. Trelaw, you're being so noisy. Dr. Ursula, are we going to have to write this proof on a quiz? No, not going to make you prove this. Use the theorem, sure. Use the power rule, absolutely. But I'm not going to make you rewrite this proof. I just think it's something that it's helpful, I hope, for you to see as just an illustration of where does this come from. Any questions or comments before we move on to our next helpful result? Okay, in that case, we flip the page. So the next kind of theorem that we're going to be taking a look at is going to be the sum and difference rules, which is going to give us a way to say that derivatives work nicely with regards to sums and differences. And so the way this result works is we can say that if f of x and g of x are differentiable functions, differentiable just means functions that we can take the derivative of, then the derivative of f plus g is going to be f prime of x plus g prime of x. And ditto with the difference, f minus g prime, the derivative is going to be f prime minus g prime. In other words, if we have the sum of two different pieces or two or more pieces, and we want to take the derivative of the whole sum as a whole, we can just take the derivative of each individual piece and then add those together. And ditto with differences. So let's do a quick example where we try and put this into practice. Let's look at the function f of x equals x cubed plus cube root of x minus 1 over x squared. Let's see what happens when we try and differentiate this. So according to the sum and difference rules, if we want to differentiate this function as a whole, we can just differentiate each of the individual terms and then add or subtract accordingly. So what are we going to get if we use the power rule to differentiate x cubed?
3x squared.
What's that?
3x squared.
Yeah, the 3 comes down in front as sort of our n, and then when we subtract 1 from our exponent, we're going to get a 3x squared term. How about the cube root of x? A little bit trickier. Maybe first of all, it might be helpful to rewrite cube root of x as being x to some power. How can we rewrite cube root of x as x to a power? Right?
X to the 1/3.
Yeah, we can rewrite cube root as being x to the 1/3, similarly to how last class we were rewriting square root of x as x to the 1/2 power. Anytime you're taking an nth root, you can always rewrite using a fractional exponent and say the nth root of x is the same as just taking x to the 1 over n. And so if we were to differentiate this x to the 1/3 power, what is that going to come out to? If we were to use the power rule on that. Hannah?
1/3 x to the negative 2/3.
Nice. So you pull down the 1/3 out in front, and then when you take 1/3 minus 1, you subtract 1 from the exponent. 1/3 minus 1 will give us a negative 2/3 power. And then since Dr. Gerstel hates negative fractional exponents, I'm going to write this out as being 1 over 3, let's say cube root of x squared. Because x to the 2/3 is the same as saying x squared raised to the 1/3, which is the same as cube root of x squared. And then the fact that it's a negative exponent means we put it in the denominator. So finally, how do we differentiate this 1 over x squared term? When?
Rewrite it first as x to the -2.
Okay, you want to write this as being x to the -2? Okay, and what happens when we use the power rule to differentiate x to the -2?
You bring the -2 in front, and then, so it would be -2 over x cubed.
Yeah, it's going to come out to, oops, wrong line. Didn't give myself enough room here. Yeah, the x to the -2 term is going to become a minus 2x to the -3. We pull down our exponent and then subtract 1 from it, which the minuses are going to become a positive. Minus minus is a plus. And then the 2x to the -3, how do we write that? How's another way we could write that one?
2 over x cubed.
We could put that as just 2 over x to the +3. So in the end, this is going to be our answer. So the moral of the story is, according to the sum and difference rules, to differentiate this sum where we have one thing plus another thing minus a third thing, to differentiate that, we can just differentiate each piece separately and then add the corresponding results together. So derivatives behave nicely with respect to sums and differences. Dr. Gerstel, what about products and quotients? Are derivatives going to behave nicely with respect to that as well? Just you wait. That's going to be standard 6. And slight spoiler alert for standard 6, we're going to have a song towards the end of it. Everybody gets to sing together. Okay, next derivative rule, just plowing through them today, is going to be the constant multiple rule. Where the constant multiple rule is going to say that if f of x is equal to a constant multiple of some other function g of x, then the derivative of f of x, f prime of x, should be equal to that constant multiple of g of x. So in other words, constant multiples are going to get, the constant out in front is going to get left alone, and we'll differentiate what's the constant's getting multiplied by separately. And similarly, we can say that if f of x equals c is itself a constant function, then f prime of x is just going to be 0 everywhere. So let's take a look at why this is, because I think this second part of the theorem's an interesting one. That if you have a function that's just f of x equals some constant, like f of x equals 2, f of x equals 4, f of x equals -1, then the derivative is always going to give us 0. So let's take a look at a graph for the second one here. Who do I want to pick on? Emily, what's your favorite number? 14. Okay, it's a big number, but we can go with that. Let's say we wanted to look at the constant function f of x equals 14. What would the graph of that look like? Our function is just it takes on the constant value 14 for all values of x. Kinsey?
Just a line.
Just a
Y equals 14.
yeah. So not only just a line, but a straight line with a y value up here of 14. So this is going to be our f of x. It's just this flat line. And since we have a flat line here, if we were to take the slope at any point along that line, let's say we were to go over here to, I don't know, x equals 2. What's going to be the slope of this function, the instantaneous rate of change at x equals 2? Yeah?
0,
Why is that?
because there's no change.
Because there's no change in y as x changes. Yeah. If we were to try and draw a tangent line to f of x at this point, a line that kind of passes through that point and matches up with the slope of the function there, well, the tangent line is just going to be the same as the function itself. It's totally flat. So, meaning there's no change in our y values as x changes. So our tangent line is going to have a slope of 0, just like the function f of x does. And so that's going to tell us our derivative at that point should be equal to 0. And in fact, since x equals 2, our choice of x didn't matter, since our original function is always going to just be a flat line. That's going to tell us no matter what value of x we look at, our derivative is always going to come out to 0. So our derivative function ends up just being this straight flat line, y equals 0. So that gives us some indication of why is it the case that if we have our f of x equal to some constant function that doesn't change, then the derivative is always going to be 0 to account for the fact that if you have something that never changes, then the instantaneous rate of change of that function is just going to be 0. There is no change, therefore the rate of change is 0. Any questions or comments? Let's look at one more example then as a class, and then I'll give you all the opportunity to work on some practice problems without me. So let's take a look at the function g of x equals, let's say 4x squared minus 3 divided by x squared plus 5. And I want to look at how can we differentiate this function. So let's start out maybe with the 4x squared piece. According to the first part of the constant multiple rule, if we're going to be differentiating a constant times some expression with x's in it, in this case 4 times the function, or times the expression x squared, according to that constant multiple rule, the 4 is going to get left alone as a constant multiple out in front, and then we will just need to multiply 4 by the derivative of this x squared term. What is the derivative of our x squared term, by the way? 2x. It's going to give us 2x, which in our next line, if we multiply that out again, is going to give us 8x. So in other words, the 4 out in front of the x squared just kind of gets pulled along for the ride when we're taking derivatives. It ends up not mattering. As far as the derivative process is concerned, it's only really the x piece that we need to worry about differentiating like this. So how can we differentiate our minus 3 over x squared term? Rachel?
Would you first take the 3? Never mind.
Never mind. Getting cold feet. Mackenzie?
You could rewrite it as 3x to the negative 2.
Okay. Sounds reasonable to me. And then Bennett?
I was gonna do something different, but it's probably wrong.
What are you gonna do?
I was just gonna say, just make it 2x in the bottom term.
Ah! Can we take the derivative of so you want to take the derivative of minus 3 over x squared and make it minus 3 over 2x? Ooh. Do derivatives behave this way with respect to quotients when we have stuff in denominators? I would say we don't know yet. So I don't think we can necessarily do this quite yet. It's going to turn out to be the case that no, it unfortunately doesn't work out to be that nice. But that's an interesting idea, Vivek. I'm glad you suggested it so we could talk about it a little bit. It's going to turn out to be the case that we can't just do that because, spoiler alert for standard 6, derivatives do not behave nice with respect to multiplying and dividing. Is this it?
Then you would multiply the negative 2 by the negative 3.
Okay.
And then subtract 1 from the negative 2.
Ooh, okay. So sounds like you want to pull out the negative 3 as just a constant multiple, and then when you differentiate x to the negative 2, get negative 2x to the negative 3?
Well, I guess I did it differently. Like I did negative 2 times that 3.
Okay. I think that would come out to the same thing.
Okay, yeah.
Is that, yeah. I treated this as just adding a negative 3 over x squared. You're treating it as subtracting positive 3 over x squared.
Yeah.
But it comes out to the same thing in
Okay.
the end. So I think what you said is going to work just fine. But yeah, absolutely. We can rewrite this as just being minus 3 times x to the negative 2. And according to the constant multiple rule, when we differentiate that, the negative 3 kind of gets left alone as a constant multiple out in front. And then when we differentiate x to the negative 2, we do the power rule. Pull down the negative 2 as out in front of the x, and then subtract 1 from our exponent to get negative 2x to the negative 3. Which, when we simplify this, is going to come out to what? Yes, Helen?
Plus 6 over x cubed.
Yeah, the minus 3 and the minus 2, we can multiply to give us a plus 6. And then the x to the negative 3, we could just write as 1 over x cubed to get a plus 6 divided by x cubed. Is that what you were going to say, Lynn?
Yeah.
Yeah, sometimes I like trying to avoid calling on the same person too much just to spread the opportunity for the rest of class to have the chance to answer. I'll go, Benedict. I don't like that. I'm a little scared by the fact that this is not equal to what you got here. Something tells me maybe your approach isn't quite going to work out, as we'll see next standard. So finally, how about this plus 5 term at the end? What happens when we differentiate that? Right?
It goes away because the derivative of a constant is 0. It's not gonna be in our derivative function.
Gadzooks. It's plus 5 is just a constant term, and according to the second part of the constant multiple rule, anytime we differentiate a constant by itself, it just goes away and becomes 0. So it's not even going to affect our final derivative, which turns out to just be 8x plus 6 divided by x cubed. Less. So in practice, when you differentiate these sorts of expressions where you're adding a bunch of different powers of x together, what ultimately ends up happening is you need to use sort of a bunch of rules in conjunction with each other. First of all, we need to use the sum and difference rules to say, to differentiate this whole expression, just differentiate each piece and kind of add or subtract them at the end as appropriate. And then to differentiate each individual term, for say 4x squared, we use the constant multiple rule to kind of leave the 4 alone and then just differentiate the x squared term. And finally, we needed to use the power rule to differentiate individual powers of x, like x squared and x to the negative 2, in order to get our final derivative. So we just kind of used all 3 of these last 3 theorems that we talked about in order to make this work out. Any questions or comments about what we did here? Okay, in that case, it's your turn. So the next couple pages of the packet have 4 sort of different functions that I'd like for you all to take a look at to see if you can differentiate using the techniques that we've talked about. So what I'm going to encourage you to do is pair off with a person sitting next to you or nearby, I'm going to encourage, but not enforce, and see if you can evaluate these next, I can show my version with the answers, see if you can evaluate the derivatives of these next 4 functions, going through the next couple pages. Go ahead, take a couple minutes, take a look at these derivatives. I encourage you to talk to your neighbors, make sure they're on the same page. And then after you've had a couple minutes to look at this, we'll come back together as a class and see what happens if we try and evaluate these derivatives. And if you feel like you've evaluated these 4 derivatives, and you feel confident in your answer, go ahead and take a look at the word problem on the second to last page.
Oh, it's so good. So it's not. I forget what it was. I was
Oh, I
We're skipping over. Let's see on the flip side.
One, and then n minus one.
Oh wait,
I always forget that the door locks.
And
You still leave it ajar.
rooms, and I was like looking at them, and I said on once, no, like looking at the orphans, and my teacher got which grade was. I noticed that, yeah, it was negative. I'm like close to kind of did, because I was like doing so bad, and then like the one thing, my teacher goes, I would get this credit if I were you. Ooh.
Ooh.
Oh, so that number goes back. Minus 3x squared, oh my
I'm
god.
still working on the board.
Okay, this is the time of my life. Okay. Mr. Salad.
Where is it?
We read a lot of books about black holes and stuff. Black holes? Okay. I don't know anything about that. Hebrew.
Yeah, I guess my one question is, x is just x to the one, right? Okay, so if we did n minus one, if we did
Yeah.
one x.
Oh.
Yeah.
Okay.
Okay.
Well, x to the zero is actually
Now-
x to zero, at least for my fragment brain. Sure.
Go ahead and take about another minute and then we'll come back together as a class to discuss. If at any point you're not sure about something, feel free to flag me down and be happy to answer any questions you have.
Okay, yeah, we'll just write that down.
Around 5.
X to the 0 is in fact 1.
Probably not next week.
In fact, that's another way to think about the derivative of a constant is 0. You have a constant, you can just write that as x to the 0 times that constant. So when you differentiate it, it becomes 0 x to the negative 1.
Okay.
No, that's right.
No, that's good. What? Not tries out. And if you do it again, it's like you get the x. I'm really speaking. How basic on
Alrighty, let's come back together to talk about a couple of these. Let's see, which ones do I want to do? Do g of x. So, function g of x was equal to 1 over x minus x cubed. So how do we differentiate that using what you all have discovered? Riley?
So we wrote 1 over x as x to the negative 1. And then just use the power rule on both. So then I got negative x to the negative 2 minus 3x squared.
Like that? Okay? Everyone on board with that? I'm on board with that as well. Except I don't like negative exponents. So how can we rewrite this expression?
Negative 1 over x squared.
Yeah, negative 1 over x squared and then minus 3x squared. For the record, like I said last time, if you were to write this line on a quiz, you'll probably get a frowny face from me, but it's just as equally correct, so you would get full credit for an answer like that. Yeah, really nice use of the difference rule and the power rule here. How about this k of t expression? 1 over t squared plus 1 over t plus 1 plus t squared. A lot of terms floating around here. How about the first term, 1 over t squared? Rachel?
You would rewrite it as t to the -2.
Okay, and when we differentiate that?
It would be -2 times t to the -3, which would be -2 over t.
Like that? I like it. Yeah. As always, exponents in the denominator you can just rewrite as negative exponents for the purpose of using the power rule. How about the 1 over t term? I'm gonna start calling on students to avoid Riley and Laura steamrolling here. Or Riley and Rachel steamroll. Okay, when?
Rewrite it as t to the -1.
Write this as t to the -1, and when we differentiate,
-1 over t squared.
we're going to get -1 times t to the -2, which becomes a -1 over t squared. Let's see. Tyra, how about our +1 term?
It's just gonna be 0.
That one's just constant, so it comes out to 0. That's pretty nice. I'm not even going to include it as part of our final answer. Helen, how about the plus t term?
The plus t term will just come out to be 1.
I think so, because t we can just write as being t to the first, whose derivative is going to be 1 times t to the 0, and variable to the 0 power is just going to be 1. So the plus t just becomes a +1. And Danielle, how about our plus t squared term?
Would just be 2t.
Well, let's see. If we pull down the t out in front and subtract 1, we'll get 2t to the first, which I do in fact agree is going to be 2t. 2t is fun to say, by the way. There we have it. Our +1 term goes away, and everything else just gets differentiated using the power rule to give us this expression. Any questions or comments on either of those examples? Okay, let's take a look at a word problem. If you are running down the road, so your distance from home, t minutes after leaving, is f of t equals t cubed plus 4t plus 1 miles, how fast are you running after 3 minutes? So this problem, we're giving another sort of real-world velocity sort of example, where we're given a function that measures distance traveled. So f of t is how many miles you are from home. And we're asked to find at t equals 3 minutes, what is the velocity / speed? So how would we find that? Yeah?
Velocity is the instantaneous rate of change at a point, so you take the derivative of the function and then put 3 in for t.
Ooh, okay. So, what you propose is that since we're looking for instantaneous velocity at a single point in time, since that's just the same as taking the derivative of the distance function, we can just find f prime of t and then plug in 3?
Yes.
Oh, yes, sir. Roughly.
Yes, sir.
Makes me feel important. Okay, so what are we going to get if we take f prime of t here? Sure, yeah.
3t squared plus 4.
Okay, so that's what we would get if we differentiated our distance function with respect to time. And so then you wanted to plug 3 into that expression?
Yes, sir.
What do we get when we plug in t equals 3 here?
31.
Let's see, we're going to get 3 times 9 plus 4, which is 27 plus 4 is 31. So that at that point in time, we are traveling with a velocity of 31.
Miles per square.
Miles per minute.
Oh, what was it minutes? Well, that's really fast.
Pedro?
31 miles per minute,
Why per minute?
because it's at 3 minutes.
Because distance is being measured in miles. Time in the problem is being measured in minutes. So this is going to give us 31 miles per minute. Which, by the way, if you're able to run at that velocity, you should try out for, I'm not even going to say the Olympics, you should try out for like the Justice League. Because you're probably the Flash. Or if you're a Marvel fan, Quicksilver. Or you have rocket boots or something. Anna, you had an interesting approach to this problem. You took the derivative f prime of t and then plugged in t equals 3.
Yes.
Yes.
Yes, sir.
For the record, you don't have to call me sir. What if we tried this instead? What if we took f of 3 from the original function, which would have given us 3 cubed plus 12 plus 1 is 27 plus 12 is 39 plus 1 is 40. And then taken the derivative of 40 in order to get 0.
That's not right.
That's not right. I don't know. At least if it's me, I feel like it's more realistic for me that I'm moving at 0, I'm not moving at all, than that I'm going at 31 miles per minute. But in all seriousness, is this something that we can do?
When you plug in 3 to the original function, that's giving you how far you are from your home, so that's like 40 miles. That's not how fast you're going.
Yeah, so 40 is certainly not a measure of velocity here. But when we differentiate the constant number 40 to get 0, is that an expression we can use to refer to our velocity at that point in time? So in other words, what Hannah did was she took the derivative of f of t and then plugged in t equals 3. What I did was I plugged in t equals 3 and then took the derivative. I'll give you a hint. One of these is correct, and one is a pack of lies. Please?
This might be wrong, but if we did the step on the right, wouldn't it just equal 0 every time, no matter what we're calculating?
Yeah, if we're plugging in a number first into a function, it would seem that we always come out to some constant value in the end, and the derivative of a constant is 0, no matter what the constant is. So yeah, I think it wouldn't matter what our original function was. If we plugged in and then took the derivative, it should come out to 0 every single time. Which doesn't feel right. Maybe for a couch potato like me, It never really does much running. Turns out that I was the liar here. And Hannah's approach is correct. So when you're looking at these sorts of word problems, or you want to evaluate the derivative at a point like this using, say, our techniques, you always have to take the derivative first without plugging things in, and then after you take the derivative, then plug in your number. So differentiate first. Then plug in your value. Because if you do it the other way around, you plug in your number and then differentiate, as Elise pointed out, that's always going to give you 0 every single time, and that's probably not something that you want. So differentiate and then plug in the value. As Hannah oh so politely pointed out. Any questions or comments on that example? Okay. In that case, let's take a look at the back page, which involves an activity that's much more to my liking, which is eating ice cream. Use this piece of chalk. So here, we're going to purchase some ice cream, and then S minutes after purchasing the ice cream, we're going to have that know what its volume is. Specifically, its volume, S minutes after purchase, is going to be 4 minus S squared plus 3S liters. And I have 2 questions. First is, how fast is the ice cream melting 2 minutes after purchase? So S equals 2 minutes. So here, our original function is describing a volume, the volume of what's left, because we tried to purchase ice cream when it's like, I don't know, 90 degrees out because it's Hillsdale in the middle of the summer. If we want to determine how fast is the ice cream melting at 2 minutes, what can we do? Tyler?
Find the derivative of g of s so that we can plug in any number, in this case 2, so then it would be negative 2s plus 3.
Okay, let me stop you there for just a second. So you want to take the derivative and plug into, why are you taking the derivative?
Well, just because what we did over there, like, it gives us the instantaneous velocity at any point.
But that was when our function was measuring distance. Here our function is measuring volume.
Okay, I guess not velocity, but instantaneous rate of change. So, like how fast it's melting in meters per minute.
Yeah. Sorry, I'm playing devil's advocate. You're absolutely right up here. Yeah, since our original function is measuring volume, if we were to differentiate, it should give us a measure of how fast is the volume changing at a single point in time. It's instantaneous rate of change of volume, which in this case will tell us how fast it is melting. So Riley, you want to plug in s equals 2 into this expression? So what would we end up with?
Negative 4 plus 3 is just negative 1 liters per minute.
Liters per minute, since liters was what the original function was measured in. And then when we differentiate with respect to time again, since time is measured in minutes, we'll get negative 1 liters per minute. In other words, it's melting at a rate of 1 liter per minute because the volume is changing at a rate of negative 1 liters per minute. Better eat it fast. Yeah. Yeah, I like it, just like what Hannah did. If we take our original volume function and differentiate, it'll tell us how fast is volume changing at a single point in time. And then after we differentiate, we can plug in s equals 2 to tell us at 2 minutes, this is how fast it's melting. So follow-up question, how can we determine how long it takes for the ice cream to fully melt?
You need to know how much ice cream you started out with.
Okay, we need to know how much ice cream we started out with. Okay, how much ice cream did we start out with? Do we have any information that can tell us how fast or how much we started out with? Yeah?
If you put at time 0, so that's when like 0 for s into g of s, then that'll tell you. So it's 4.
Ah, so since g of s tells us how much ice cream we have after s minutes, if you just plug in s equals 0 minutes, that'll tell us how much we started with.
Yes, sir.
This is going to be our running thing. Yeah, that's absolutely right, though. So we could say, so the question was, how long does it take to melt? So we can say we start with g of 0 equals 4 liters. And I like how you all use the original function g of s rather than g prime of s, because g prime of s could tell us how fast is it melting at the start, but g of s is going to tell us what's the volume at time 0. So what can we do if we want to determine how long it takes to fully melt? This one's a bit trickier. I'll give you a hint. One of these two functions we have, g of s or g prime of s, should be equal to some constant at the point in time where it's fully melted. So when the ice cream is fully melted, what can we say at that point in time? What can we say about its volume? I heard someone say.
It would be 0.
Okay. We know that when the ice cream's fully melted, it should have a volume of 0 liters because it's melted. It's now just goop. So if we want to find the point in time where g of s is 0, what can we do?
Plug 0. Substitute g prime of x as 0, so it'd be 0 equals negative 2s plus 3.
Ah, so you want to use the derivative?
Yeah.
But I think Rachel's suggestion was she wanted to have the original function g of s be 0. Is that right?
I didn't say that, but that's what I was.
You didn't say that? I'm putting words in your mouth? My apologies. I think what we want to do here is, since the point in time where it's fully melted is where the volume is 0, the velocity might actually, the rate of which it's melting is probably non-zero because it's just fully melted away. It's been melting. So I think here we actually want to set g of s equal to 0. Which, if we do that, we'll get 4 minus s squared plus 3s is equal to 0. Which, if we factor, is going to give us negative s minus 4 times s plus 1 is going to be equal to 0. And so if we want to find what's the point in time S at which G of S is 0, in which it's fully melted away, what answer would we get for S here? If we tried to solve this equation for S.
We get 4 and -1.
We get S equals 4 and S equals -1. Gadzooks, we've got two numbers. Which one do you think we're going to want to use?
4 because your time can't be negative.
Yeah, it doesn't really make sense here for time to be negative in this example. I guess you could say, what's its volume 1 minute before I purchased it or something, but doesn't really make sense. So we're going to use S equals 4 here and say that our answer is going to be our ice cream is fully melted after 4 minutes. By setting G of S equal to 0, because we want to know when is the volume of our ice cream coming out to 0. Moral of the story is, eat your ice cream fast in hot weather. All right, that's it for Standard 5. When we come back on Monday, we'll have a quiz and then start Standard 6 and look at how do derivatives behave with respect to products and quotients. Hope y'all have a good rest of your day. See y'all on Monday.